the first thing in the understanding of laser heat source is the heat source itself. So the various distributions are possible. If you have a laser set up experimentally, you might have seen uh, they tell you the intensity distribution possible with the given laser heat source. They are like a flat intensity distribution or the hmm, top head type of intensity distribution. One of the famous is like a Gaussian intensity heat distribution that gives very high intensity at the uh, middle of the beam, at the center of the beam, and gradually it will reduces towards the edge of the beam or radially. I can see. If I will say ki beam is, let's say, circular, so the highest intensity we will see from the top view at the center, and it will gradually reduces towards the edges of the beam. So that will follow Gaussian distribution, and we will model only surface heat flux. In the last slide, I show you a machining portion. What is seen, laser is absorbed only up to few micrometer, or I can say few nanometer of the depth. When the laser beam incident on the surface, it is not absorbed throughout the volume of the workpiece. It is just a surface phenomenon. So that's why it is very reasonable to model this heat source as a surface heat flux, not as a body heat flux. Body heat flux tries to heat up whole body at the once, but laser heat source is not like that. Intensity is definitely very high, but the absorption is not throughout the volume. It is just on the surface. So as far as this heat source is concerned, surface heat flux is the better modeling technique than the volumetric heat flux. Maybe if you are going to solve some other problem, maybe this is not feasible. You need to go for the volumetric heat source. So as far as this context, surface heat flux is something which will perfectly model the laser heat source. And one of the famous, as I stated, Gaussian profile. So we'll try to understand Gaussian profile in detail. But if you have any other profile and equation for that, it's fine. Whatever way I am going to explain in terms of subroutine, you can change this equation in your subroutine according to what kind of laser heat source you have. So this is the equation for the Gaussian heat source. Let's say if you have top head or flat kind of thing, and if your machine vendor provided you what kind of equation that laser heat source follow, you can just write that equation in your subroutine, and the subroutine is just okay. Whatever file I am going to provide you, according to your need, you can customize it. So in this formula, this Q is a heat flux. Heat flux is like joule per meter square, means it's the heat energy per area, as this is the surface heat flux. So P denotes the laser power. Omega, already stated here, the 2 omega is the beam diameter. So omega is the beam radius. Alpha, that is the material parameter, absorptivity. Whenever some laser heat incident on the workpiece, the whole heat will not be absorbed. Some will be reflected, depend on the metal property, because some metals show very high reflectivity. Some will absorb more, some will emit, like that. So this absorptivity is a material constant. You will get for the given material, this value will get in the literature. In this context, whatever property, whatever simulation I am going to show you, that is mostly for the very famous aerospace alloy, biomedical alloy, that is a titanium alloy, Ti6Al4V. So for that alloy, the properties are already taken from the literature provided in the input file. So most of the simulation data you will see around this material. So that is the titanium-aluminum and vanadium alloy. It's a very famous biomedical and aerospace alloy. But again, if you have different material, whatever files we are going to provide you, that are perfectly okay. You need to just change the material, your material parameters. So as I was explaining, this absorptivity is a material parameter. X and Y showing the coordinates of the FE model. And P again, laser power is stated by the machine itself, what kind of laser power we are going to use. So in this equation, only the X and Y quantity will be updated in the simulation continuously. As we are saying, this is the moving heat source. So X and Y coordinates are not stationary now, they will continuously update. As the source will move, the coordinate system is moving actually. So this X and Y coordinates will move. So Z is not here because I already told you this is surface heat flux. We are only talking about the plane. Okay. So along the Z there will be only conduction that will be taken care by FE model, the conduction model, heat transfer model. We need not to deal with the heat source.